Let's dive into the fascinating and honestly pretty powerful world of fluids. They're absolutely everywhere, from the air filling your lungs right now to the tech that can lift a car off the ground. They shape our world in ways we hardly ever think about. So, to get us started, here's a little question for you. Think about the air all around you, and then think about that thick, goopy shampoo in your shower. They seem like polar opposites, don't they? But in the world of science, they actually share a secret identity. Any guesses what it could be? Well, the big reveal is they are both fluids. You see, scientifically speaking, a fluid is just any substance that can't hold its own shape when you push on it. It just flows. It can't resist what's called a shear force. And that's why both liquids, like your shampoo, and gases, like air, fall into the same category. They're always moving and changing shape. Okay, so we've got the basic definition down. But here's where it gets really interesting. Scientists don't just throw all fluids into one big bucket. They classify them based on how they behave, giving them these distinct personalities that help us figure out what they're going to do next. First step, let's look at steady versus unsteady flow. Picture a calm, gentle river, just flowing smoothly along. That's steady flow. The speed and pressure at any one spot stays pretty much the same. Now imagine crashing ocean waves or a wild, gusty wind. That's unsteady flow. It's chaotic, unpredictable, and always changing.
Next, we have a fluid's internal friction, which is a fancy way of saying viscosity. But really, you can just think of it as thickness. A highly viscous fluid, like honey or that shampoo we talked about, is thick and resists flowing. A non-viscous fluid, though, has almost no internal friction and flows super easily, like water.
But it's not just about how fluids act. To really get them, you have to look at their DNA. You know, the fundamental properties that make them what they are. This is the basic code that dictates everything about them. And it really all boils down to three of the most important properties you need to know: density, viscosity, and pressure. Let's break each of these down real quick. So first on the list is density. This one's pretty intuitive, right? It's simply how much stuff or mass is packed into a certain amount of space or volume. A fluid with high density has a whole lot of matter crammed into a tiny area. Now, we just talked about viscosity as a behavior, but it's also a core property. It's the built-in measure of a fluid's resistance to being moved or stirred up. The higher the viscosity, the more work it takes to get that fluid moving. It's part of its fundamental identity. And finally, we've got pressure. This is all about the amount of force a fluid pushes on a specific area. Now, you're gonna wanna remember this little formula here. Pressure equals force divided by area. Seems simple, I know, but trust me, this little equation is the key to unlocking some truly mind-blowing real-world tech. Okay, so we've got behaviors, we've got properties. Now let's try to organize all this into a kind of fluid family tree. This is how scientists categorize fluids to help them build models and make predictions, separating the real-world stuff from the purely theoretical. The first big branch on our tree splits fluids into two camps: real versus ideal. Real fluids are, well, all the fluids that actually exist, like water, oil, you name it. They all have at least some viscosity. Ideal fluids, on the other hand, are a physicist's dream. They have zero viscosity and can't be compressed. They don't exist in reality, but they're super useful for simplifying the math in scientific models. Now for a distinction that is just so cool: Newtonian versus non-Newtonian fluids. A Newtonian fluid, like water, is predictable. Its viscosity, its thickness, stays the same no matter what. But a non-Newtonian fluid, it's a total rule breaker. Its viscosity changes when you apply stress. The classic example is oobleck, that cornstarch and water mixture. Push on it slowly and it flows like a liquid. But punch it, bam, it instantly turns solid. Its properties literally change with how you interact with it. All right, enough theory. Let's connect all this to the real world. We're going to take just one of those core properties we talked about, pressure, and see how it lets us do something that seems like pure magic: lifting an entire car with a tiny little push. The whole secret, the entire trick, lies in understanding what pressure does inside a contained fluid. This one single concept is the foundation for the entire field of hydraulics. This is all thanks to a golden rule called Pascal's law. And what it says is basically this: if you apply pressure to a fluid in a sealed container, that pressure spreads out perfectly, evenly, everywhere. It doesn't get weaker, it doesn't fade away, it's the same in every single nook and cranny of that fluid. And here is how we can use that law to our advantage.
First, you apply just a small force to a small piston. This creates pressure inside the fluid. Thanks to Pascal's law, that pressure travels through the whole fluid completely undiminished. Then, that same pressure pushes up on a much larger piston. And because the pressure is the same but the area is bigger, the force that comes out is massively amplified.
And here's the beautiful math behind the magic. The pressure on the small side, force 1 over area 1, has to equal the pressure on the big side, force 2 over area 2. So, if you make the output area way bigger than the input area, you get a much bigger force out on the other side. You've just become a force multiplier.
And this isn't just some neat physics trick. It is the technology that powers so much of our modern world. That hydraulic lift at the mechanic shop, Pascal's law. The brakes that stop your car, that's it too. The flight controls in a giant airplane and all that heavy construction machinery, you guessed it, all running on this one elegant principle of fluid pressure.
So you see, by understanding the fundamental properties of something as common as a fluid, we can harness its power to build some truly incredible things. It really makes you wonder, doesn't it? If a simple fluid can do all of this, what other amazing secrets are just hiding in plain sight in the materials we see every single day?